Alrighty, now that you have been introduced to the Fundamental Theorem of Calculus Part 1, we are going to do a practice problem to reinforce the concept. So first of all, what they are asking us to do is to sketch a region on the grid provided and to use known geometric shapes to evaluate the integral from 2 to 5 of x plus 2 dx. So x plus 2 is a line, and we're just going to draw this line with a slope of a 1 and a y-intercept of 2. So here is my line, and then they're asking us to integrate from 2 to 5. So what that means is I need to draw a known geometric shape on the interval from 2 to 5. So I have one bound at 2 and the other over here at 5, and it looks like I have a trapezoid. And I'm going to find the area of this trapezoid by taking 1/2 the height, which is the distance from 5 to 2, or 2 to 5, which is 3. 5 minus 2 is 3. And then the first height, height 1 at 2 is 4. And the second height, the height at 5, is 7. So I have here 11 times 1/2, which is going to get me 16.5. All right, in the next section, we are going to write the integral as the limit of a Riemann sum. And it says here to evaluate. We are actually not going to evaluate this by hand. We no longer do that in this class. It is something we should have deleted off of your notes, and we apologize for that. But remember, when we write an integral as a limit of a Riemann sum, we always start with the same exact notation to begin with, which is a summation from I equals 1 to n and taking the limit as n goes to infinity. What that means is that we start at the first rectangle and we count the area of n rectangles, and then we take the limit as that number of n rectangles goes to infinity. The first part that I'm going to do is take the distance between 2 and 5 as my delta x. So my delta x is going to be 3, and I divide that by n, and that's going to be the width of each of my rectangles. And then the height of each rectangle is going to be this x plus 2, but recall that for x, what we have to plug in is the lower limit of integration, which is 2, plus I divided by n. And remember that what this does is it gives you the numbered rectangle divided by all of the rectangles added to the lower limit of integration. So it starts you right here at 2, and then you are going to add, say it's the 10th rectangle, out of n rectangles, it counts you over 10 rectangles on your journey from 2 to 5. So it gives you your left-hand side of the rectangle, and then the 2 adds to the height to get the y value, or the height of the rectangle, and then you multiply by this width, which is the total width of 3 divided by n. So this is the Riemann sum for this problem. We are not going to evaluate it by hand, but we are going to use the fundamental theorem of calculus to evaluate the integral from 2 to 5 of the function x plus 2. So what you did up here in known geometric shapes, we're going to show you how to do this with the FTC. Now we know by the FTC that this is equal to the antiderivative. We're assuming this is our function little f. So if we take the antiderivative at 5 and subtract out the antiderivative at 2. But the problem is we don't know what the antiderivative is, so that's actually what we have to find. Since this is f, we are going to antidifferentiate at this point just using guess and check because we don't know u substitution yet. So we will integrate using the power rule to get x squared over 2 plus 2 times x. And then we need to evaluate this at both 2 and 5. So we put this vertical line here in. This is the such that line in math. So we're basically saying take this expression such that, starting at x equals 2 and going to x equals 5, which means that we first take the 5 in for each x value. So we have 25 halves plus 10. That is going to be f of 5, big F of 5. And then we subtract out this expression evaluated at 2. So when I plug 2 in for each x, I subtract out first 2 squared over 2, which is 4 over 2, which is 2, plus 2 times 2, which is 4. So now when I simplify this, I get 12.5 plus 10 is 22.5, 22.5, minus 6, which gets me to 16.5, which is exactly what I had when I took the known geometric shapes. Now, the beauty of understanding how to do this work with the fundamental theorem of calculus is that you can apply this for any function for which you can find the derivative. You do not have to rely on, as with this function, knowing that there are known geometric shapes under the curve. So this process, the FTC, could be used for a quadratic or a sine curve. And it basically is a nice workaround to having to do the limit definition of the derivative, definition of the integral. If we had plugged this into the calculator, we would have also gotten that this expression is equal to 16.5. But it takes quite a long time to do that, so we don't want to do that, and we can use the fundamental theorem of calculus. And now we can also use the FTC for using properties of integrals to solve a problem like this, which is a really standard problem, multiple choice type problem that you might see on a test or the AP exam. Same function, x plus 2, we are integrating from 3 to 7, and we're saying that it equals 28. Now, I could have done this with known geometric shapes to show that that is actually 28, but what's interesting is that I can say that if big F of 3 is 10, I can find big F of 7, and this is just by stating the FTC, and that is that the integral of x plus 2, that's a 7 right there, the integral of x plus 2 dx from 3 to 7 is the same thing by the fundamental theorem of calculus as big F of 7 minus big F of 3. And so since I know that the integral is 28, and then they are telling me that big F of 3 is 10, I can just use basic algebra to find that big F of 7 must be the number 18.